Okay, let's take a look at routing policy. Now, remember I said earlier that if you control your routing protocols, if you can control your routing, then you can control the flow of traffic on the network. Okay, so routing policy is one of those things that we use to control routing, to control the flow of routing information. Remember, one of our goals in networking is to get the right routing information into our routers. And if we can control what information goes into the routing table, then we can control how the traffic will be forwarded. So let's look at routing policy. And because routing policy is one of those things that enable us to control the flow of traffic between, or the flow of routing information between our routing devices, and therefore control the flow of traffic. So after successfully completing the chapter, we're going to look at being able to describe the framework of routing policies, how routing policies are evaluated by the router, look at situations where we might use them, and write and apply routing policies. Okay, so let's have a look at a situation where we might want to use those. So let's look at what they are first. So a routing policy controls the flow of routing information to and from the routing table. Okay, so it is the routing table that is sort of like the core aspect of this routing policy. And we're going to use the policy to accept, reject, or modify the attributes for routes. So routes that are either received through dynamic routing protocols, sent to dynamic routing protocols, or installed in the forwarding table. Okay, so the basic concept here is that routing information is sent to other routers and received from other routers. Okay, so what routing policies are going to allow us to control is what we send to other routers and what we accept from other routers into our routing table. Okay, that's essentially what we're doing here. So here we have our routes, we've got our neighbors, and we've got our protocols. So what we can do with these routes, we can import them into our routing table, or we can decide to export them and send them out to other routers, neighboring routers. We can also export them out of our routing table and put them into our forwarding table, which is going to control the flow of traffic through our router. Okay, so there are already policies there. There are already default policies built in, already configured. This is just how these protocols work by default. They're already there. But we can change these defaults, okay? But these are the defaults. So with BGP, BGP will accept all BGP routes and import into the inet.0 table, which is the master IPv4 routing table. So the export policy is to accept all active BGP routes. So okay, so with BGP, any routes that are advertised, any BGP routes that are advertised to us, to our router, we're going to accept them. And any BGP routes that we have in our routing table, because we have accepted them, we will re-advertise out to other routers. Okay, so everything goes in, everything's accepted, everything's re-advertised. With OSPF, we will accept all OSPF routes and import them into inet.0, but we're going to reject everything. So we're not going to advertise any OSPF routes by default, 0, to anyone at all, ever. That's the default policy. Okay. ACIT accepts all routes and imports them and rejects everything. Doesn't re-advertise any at all. We haven't really talked about ACIT. I know it's sitting there, you think, oh, what is that? It is another routing protocol. It's a linked state routing protocol. It's similar in a lot of ways to OSPF. Okay. It's used by a lot of the bigger carriers, bigger internet service providers. A lot of the tier ones actually use ISIs. And RIP, policy for RIP is accept all routes from explicitly configured neighbours. So in other words, we're only accepting routes from the neighbours that we say we're going to accept routes from, but we're not going to re-advertise any RIP routes at all. Okay, not at all. Okay, so that's our default policies. Okay, so BGP, we accept all, we re-advertise all. OSPF, we accept them, we don't re-advertise anything. Same goes for ISIS, and with RIP, we only accept from the routers that we say we're going to. So in other words, you have to specifically say whether you are or not. If you don't say, then no RIP routes will be accepted at all by a Juniper device. It says, we don't care, we're not interested in RIP routes. You keep your RIP routes, we don't want to know about them. Unless you specifically say, actually, we do want to receive RIP routes from a particular device, then it will. Okay, so we can build our routing policy by using matching criteria, and essentially our goal here is to select what routing information we either import into our routing table or export from our routing table. That's our goal with the routing policy. That's what we're trying to achieve. So we've got 0 or more terms. Software evaluates the term sequentially until it reaches the terminating action or the end of the policy. The from statement describes a match condition. So if I say from, that is a matching condition. If it matches the from, then the action will be taken. So what happens is we create this policy, we give it a name, we put some terms in it, we create some matching criteria within our terms. Then the then statements, as I said, are the actions that are taken when a match occurs. We can have a number of terms that we put into our policy. All the terms are evaluated sequentially. Okay, this is probably sounding a lot like an access control list so far. Okay, so it's got some similar ideas to how an access control list works. Okay, so what can we match on? Common matching criteria for routing policy. We can have a routing prefix, a network number, which is known as the prefix. So we can also use a thing called a route filter or a prefix list. We're matching on a number of prefixes. We will match on a protocol. So we're going to say we will accept OSPF routes or static routes or BGP routes or whatever they are, whatever the protocol is that we're matching on. And what we're trying to do here is either import or export from our routing table. And then there may be some attributes that we're matching on. It may be an area. We may say, well, we will accept routes from OSPF area 0. Or if it's BGP, we may be matching on a particular autonomous system path or a particular BGP community. So a path, AS path, and community are attributes of BGP routes, whereas an area ID is an attribute of a OSPF route. They will have an area associated with it. We can match on the next hop address. So there's certain things that we can match on. If we're going to create a prefix list, so within our policy, instead of just having a particular one network that we're matching on, there may be a list of networks that we want to include in this routing policy. In that case, we can create a prefix list, give it a name, and put a whole bunch of networks in there. Here's a prefix list here. It is 10.0.0.0.8/8, 172.16.00/12, and 192.168.00/16. If you look at those, you will realise that they are all private ranges, or IPv4 private network address ranges. And the prefix list is called RFC 1918, which is actually the RFC that describes those private ranges. So I could have called it anything. I could have called it Mickey Mouse. It still would have worked, but it's a pretty more descriptive name. Then we have a policy. So we've got this prefix list here, and now I am going to reference that list in my policy statement. So I'm going from, which is the matching criteria, prefix list RFC 1918, then reject. So in other words, if I get any routes from any of those networks, I will not be accepting them in my routing table. Okay, now, if you are a router sitting out on the public internet, that would be a pretty good policy to have, because you should not be getting any routing information regarding those private networks out on the public internet. So what we're accepting or rejecting here is routing information, okay, routes that we receive. That's what we're filtering on. Then we might have a policy statement, policy 2, from prefix list filter RFC 1918 or longer reject. So we'll look at this, what this or longer means here. So the prefix filter allows a match types and action supported match types are exact, longer, and or longer. We're going to talk about what exactly those are. So what we're trying to do is identify the routes to which networks we're either going to accept or reject in this policy. Okay, so a route filter will match individual routes within a policy. You specify multiple route filters within a single term. So essentially, if I were to say reject, just create this term here and say term reject RFC 1918 prefixes, and then say from route filter 172.16.0.0/12 or longer. I'm going to reject that. I'm going to reject this one. I'm going to reject the last one as well. What that does is it matches on anything with a /12 or longer. So it could be any network that matches the first 12 or more of that particular prefix. So the first 12 bits or more of that first prefix will be a match. Of the 192.168.00/16, it's the first 16 bits or more will match that particular criteria, and on the 10.0.0.0/8, it's the first 8 bits or more will match that particular criteria. Okay, so that's kind of the or longer. We'll take a look at that concept a little more soon. You can have an exact match, so it has to be 192.168.0.0 exactly. So what we're talking about is routing information that's coming through. Longer simply means it has to be longer than /16 and up to. This means it can be from 16 up to 24, so you can have like a particular criteria in there. If you take a look at, you can have a prefix length range. If you take a look at kind of how this works, if we say 192.168/16, if I say it has to be an exact match, then I'm only matching this little bit of information up here, this very specific routes. So if I get routing information for exactly that, then that's what I'm matching against. If I go or longer, that I'm matching against everything from 16 right down to 32. If I just say longer, then it has to be longer than 16. So really I'm starting at, well, 17. Oh, sorry, yeah, 17 and going down to 32. If I go up to, then I'm saying going up to, say, 24, then I'm not going all the way to 32, I'm only matching up to 24. If I have a range, then I'm matching on a block within that particular range. So what exactly is this information that's coming through that I'm matching on? It's route advertisements. So these routes are being advertised from other routers into this particular router, and what we're trying to decide is, do I accept or do I not accept those routes into my routing table? Or conversely, I could be deciding, I've got routes in my routing table, do I advertise or not advertise those routes? And the routing policy can determine exactly what you advertise or not. Okay, so you are selecting, you're actually being selective on the routing information that you're either allowing in or out of your routing table. That's the point of this routing policy. You will do a lab on it. It will make more sense when you do the lab. Okay. What are the actions we can accept or we can reject? We can divert to the next term or the next policy to be evaluated. We can modify. Here's another thing we can do. We can modify the attributes as we either import or export from that. What about if I'm getting a default static route being advertised to me from somewhere else, from another router? Okay. I could say, well, that's good. That's a good backup default route, but I don't want it to become my primary default route. So what you could do is you could, as part of the process of importing it into your routing table, you could modify the route preference on the way in so that it would then become a higher number and therefore less preferred, so that it would still be there, but it would only ever become active if your more preferred static route was no longer available. Okay? Or what you might do, you might be advertising a static route to another network, and that network's or default static route to another network which already has a default route, but you want to provide an alternative path for that default route to that network. So when you advertise the route, you change the preference on the way out of that network. You change the preference on the way out of that network so that when that route arrives in the other network and is imported, which is the default policy, it will not become active unless that network loses connectivity to its current default static route, or static route path. Okay, so here is here's us defining a routing policy. So it's under the Edit Policy Options hierarchy. We're creating a statement. It's called My Policy. It could be called anything, but it's called My Policy. We're creating a term which says accept local route from protocol direct. This is a directly connected interface, and the interface is GE000. Then accept. Okay, so we're creating this policy. We've accepted this by our policy. We've got another term here which says accept some static routes. So here I have a route filter which references some static routes. Then accept, and now we're accepting some RIP routes as well. So here's my policy. Statement is called My Policy. So now that I've got this policy, then what I do is I can apply the policy as either an import or an export policy. So here I'm applying the policy to the OSPF protocol as an export policy. Now, what is that going to do? Well, what it's going to do is it's going to take that directly connected route, it's going to take those static routes, and it's going to take those RIP routes, and it's going to export those into OSPF, and it's going to cause my router to advertise those routes out as OSPF external routes. So now, those routes will now be advertised by the OSPF protocol. Okay, so I've actually taken direct routes, static routes, and RIP routes and put them into OSPF. So OSPF is now propagating that routing information, okay, through OSPF. So all my OSPF routers will then receive that routing information. All right, so that was the result of that particular routing policy. So the flow of a routing policy is we have a policy, we have terms, it's accept or reject all the way through. We can actually feed that through into another policy as well, and so on, and kind of daisy chain those policies together. Okay, let's take a look at a case study where we may want to use a routing policy. So our goal here is to advertise the default static route defined on R1 into OSPF using a routing policy. So R1 has got a static route, it goes out, it's connected out to the internet. But none of the other routers have a direct connection to the internet, only R1 does. So if any of the networks that are, or any of the subnets that are connected to any of these other routers to get internet access, they're going to have to know about that static route that's on R1. So I have a few ways of doing it. I could go and individually configure default static routes on R2, R4, and R3 to say, hey, your default static route is over here. Go and over to R1. Okay, so I could point the traffic or send the traffic over to R1. That's one way of doing it. Alternatively, I could go onto R1 and I could export my static route into OSPF, and then OSPF will automatically advertise that static route around the rest of my network for me. It's the other way of doing it. Okay, so let's do it the second way. So we're going to do a show route protocol static, and what we are going to see here is we've got a default static route, which is, there it is, all good. Now, how do we go about advertising that static route? Or how do we go about making OSPF advertise that static route? So we go under Edit Policy Options. Policy statement is called Default Static. The term is Accept Default Static from Protocol Static. Route filter is 0.0.0/0 exact. So we're looking at that exact route, which is our default route. The action is accept. There's my routing policy. Done. That's it. Configured. Okay, that's my routing policy. Now I need to apply my routing policy. So I'm going to go over under Edit Protocols OSPF. I'm applying it as an export policy. So I'm going to export the default static policy. Okay, what's going to happen as soon as I've done that, R1 is going to flood an external link state advertisement for the default static route to all the other routers. Okay, so within OSPF, there is a certain type of link state advertisement, which is an external LSA. And that's saying, hey, I've got a route which was not calculated by OSPF. This is not an OSPF route. In other words, I didn't figure this out for myself. This was imported into OSPF from somewhere else by a policy. So it becomes an external LSA, and that then gets advertised around. So now if I go over to R4, for example, and do a show route protocol OSPF exact 0/0, I'm going to find that I have got my default static route. OSPF, you notice that the preference is 150, preference is 150, okay, whereas the default preference for OSPF on a Juniper device is actually 10. Okay, OSPF has a preference of 10. Over here, I've got a preference of 150. Why is it 150? Because that is an external OSPF route. It was imported into OSPF. It is not a native OSPF calculated route. Okay, it was imported in. And I have actually got two next hops for that. I've got one via R2 and one via R3. Okay, because R1 advertised it out to R2 and R3, and R2 and R3 have both advertised that default static route out to R4. So R4 has received two link state advertisements for that route, one from R2, one from R3, and there they are listed right there. Okay. That is a use of routing policy. Okay, identify a route, my static route, my default static route, accept it, apply it to the OSPF, and then make OSPF re-advertise that route out. So what I'm saying is, by default, OSPF would not be re-advertising my static routes, okay? But by routing policy, I can make OSPF re-advertise my static routes. Okay, so in this chapter, we describe the framework of routing policies, looked at how software evaluates routing policies, identified situations where you might use a routing policy, and wrote and applied a routing policy. Okay, let's look at some review questions. What is routing policy and when might you use it? Okay, so just thinking about that example, right? We used a policy to match a particular route. The action was accept. So now we're accepting that route, which in this case was a static route, a default static route. And then what did we do with it? We applied it to the OSPF protocol. We could have applied it. So what routing policy does, it controls what we export out of our routing table into other protocols and what we import into our routing protocol from other protocols. So it controls what comes in and what goes out. The other thing we can do with it is we can modify the attributes of routes as we import them or as we export them. For example, I could have said, well, yeah, I'll export that static route out, but I'm going to change the preference of that static route. I might change it to 7 instead of 5. Or just in case those other routers already maybe they've already got a static route somewhere else. I don't know. Maybe they do. Okay, so I could change the preference on it so that, well, if there's a static route in there already, a default static route, it would normally have a preference of 5, therefore that would become active. But if it doesn't have one, then the route I am now exporting would become active. So you can do it like that. So you can change the preferences on the way in or on the way out. That would have been something we could have done as part of that policy. We could have just gone in there and referenced the preference and changed it as part of our routing policy. So you can control, basically what we can do with routing policy, we can control the flow of routing information between our routers, which in turn controls the flow of network traffic. Some components of a routing policy. Well, there is terms. Terms have got a matching criteria like the from, and they've got an action, which is the then. So from is a matching, then is an action. Two main steps involved when implementing a routing policy. What are the two main steps?
receive, send, and install. And they receive, then send, and then install the policy.
Well, when we're implementing, excuse me, a routing policy, what we have to do first of all is create the policy. So that's under Edit Routing Options is where we create the policy, and then we apply the policy. So the policy in our case was applied to the OSPF protocol. So that was under the Edit Protocols OSPF hierarchies where we went and applied it. So we create it and then we apply it. They have the two steps. Okay. How are we doing for time? 3 o'clock. Alrighty, let's look at our next lesson. So that was routing policy, and there is a lab on that you are going to do. Okay, let's go and close that one. Oops, get rid of that. Okay, now let's take a look at something which has a completely different purpose, but is quite similar in the way that we construct it. So we're going to look at firewall filters. Firewall filters. Okay. So, a firewall filter. Now, we've come across these things before when we did our Cisco course, except in Cisco, they are called access controllers. Okay, in Juniper, they're called firewall filters. They are, in fact, exactly the same thing. They do exactly the same job. Of course, being a different operating system, we write them a little differently. There's a different way of going about constructing them. So we're going to look at describing the framework of firewall filters, how they're evaluated, where we might use them. We'll write and apply one and describe the operation of another little thing which is called unicast RPF. So we'll look at that as well. Okay, so let's do an overview of firewall filters. So they control the traffic entering and leaving a network device in a stateless fashion. What does a stateless fashion mean? What do I mean by that? If it wasn't stateless, what would it be? Stateful. Okay, so we've got stateless and we've got stateful. Okay, what is the difference between those two things? Any ideas? Stateless, stateful. Huh? Okay, well, I suppose it's probably easy to talk about stateful, and then we know that's not, and stateless is not that. Okay, so stateful, if we have a stateful filter takes into consideration the entire communication session. So it takes into consideration traffic that's going to the destination and traffic that's coming from the destination. So it considers the flow of traffic, the two-way flow of traffic, as a single entity and treats a flow of traffic as one thing. So with stateful, if I say I'm going to allow this communication process, so I'm going to allow connectivity to a certain endpoint or from a certain endpoint, then whatever the return traffic is also permitted as part of that particular process. With stateless, it doesn't take into consideration at all the return traffic. It just takes a look at each individual packet as it goes through the interface in a particular direction, and it evaluates the firewall filter requirements based on one packet, each packet as it goes through. It gets individually evaluated. So it's taken on its own, and there's no consideration of what communication flow that packet is part of. That's irrelevant to a stateless filter. So a stateless filter looks at each packet on its own merits, and it doesn't take any regard to what communication that might be a part of. So it processes every packet independently, and we can use it to filter and to monitor network traffic. So this looks very familiar, doesn't it? First term, second term, etc., etc. And it is very familiar. So building blocks of a firewall filter, kind of very similar, except a very different purpose. We are here evaluating traffic through an interface. When we were building routing policies, we were evaluating routing information via route advertisements that we were either sending or receiving, that were either coming into or going out of our routing table. So it's a very different purpose for these two things, even though they look quite similar. So we've got one or more terms, software evaluates the terms. We have the from statement, which is the match. We've got the then statement, which is the action, and we've got a bunch of terms. Now, one thing to be aware of is that there is a default discard in a firewall filter. So if nothing matches, then everything is rejected. It's basically how it works. If I don't get a match, the filter will stop all traffic. Okay, so what can we match on? Well, pretty much most header fields, source address, destination address. We can look at layer 4 stuff as well, source ports, destination ports. We can look at application layer ports like telnet, etc. We can have match condition categories. We can have a range. We can have addresses. We can have bit fields. So there's quite a lot of different things we can actually match on. So what are some of the actions that we can take? Accept, discard, reject. So they are the three things we can do. We can also have flow control, where we can put send the traffic over to another term. And we can also have modifiers, actually modifiers. Maybe we'll count the traffic, maybe we'll log the traffic, maybe we'll change the forwarding class and lost priority of traffic. That's kind of handy. That has to do with a thing called class of service, which we will look at later on. So what we're really doing there is we're changing the priority of traffic. So we may look at information that matches our particular filter, and then we may modify the attributes of that traffic. So we may say, well, I'm going to change the forwarding class. I'm going to change the loss priority of that particular traffic. We can have a policer, where we look at how much traffic is coming through, and we can cut off the traffic after it reaches a certain bandwidth. So or we can reduce the available bandwidth on traffic that goes over a certain bandwidth. So we can identify how much traffic. One important point here is that everything that is not explicitly allowed is discarded. So it's exactly the same as an access control list in that regard. Okay. How do we implement a firewall filter? So it is under the edit of firewall hierarchy. In this case, under edit firewall family INET, so this is going to be an IPv4 filter in this case. Otherwise it would be INET 6 if it was IPv6. So we are setting up a filter. The filter is filter in. The term is block some packets from source address 10.10.10.0/24, then count spoof in, and then discard. So we're actually doing a count, putting it into a file called spoof in, which is where our count is going. And then the final term is accept others, then accept. So you notice on the final term, there is no from. There's just an action, which means everything matches. It matches everything, okay, because there's no specific matching criteria there. Okay. Alrighty, so once we've created our firewall filter, now we have to apply it, and we go and apply it on an interface, just like an access control is. So here's our interface, and we are going under filter, and this is an input filter. It's called filter in, and we're creating an output filter called filter out in this case as well. So apply the filter to the interface, and then a little point here about when you are applying these filters, really good idea to use the commit confirmed statement, because you might inadvertently end up locking yourself out of the device with your firewall filter. So commit confirm will kind of avoid that situation. And there we are, we apply the filter onto the interface. Okay, let's have a look at this little scenario here. So we want to apply a filter on R1's GE00.1 interface to allow HTTP traffic to 172.27.102.100. So we're going to allow that traffic, and we should apply it as an, okay, so should the filter be applied as an input or output filter? What do you reckon? Okay, so we've got the server over here, .100. We're putting the filter on GE001, which is over here, the one that's attached to the internet. Is that an input? We are going to allow traffic. Is that an input or an output filter? That's an input filter, yeah. It is an input filter. The traffic is going into the interface. So here we have here's a filter. So look at this one here. Which inbound traffic does the router permit? So here we have a web filter. The term is allowed web traffic from destination 172.27.100/32. That's the destination address. Protocol TCP, port HTTP, then accept. So the destination address is in fact our web server. Then we have another term which is deny the traffic. So from protocol TCP, port HTTP, then discard. So good. And what are we doing? We're applying it as an input filter on R1. Which inbound traffic does the router permit? What do you reckon? What traffic will that router permit? Well, it will permit any traffic that's going to 172.27.102.100. That's what it will permit. Okay. Will it permit any other traffic? Is it going to permit anything else?
That's only one. address.
There's only one address, yes. So that's all it's going to permit. So any traffic that's going to 172.27.102 will be permitted, and that is all. That is all that will be permitted, because that's the only thing that matches a statement in that filter, okay, with an except after it. So yeah, if you wanted to permit anything else, just go back up, you need another term under there, which said, which then had a then except. You'd have to just put another then except on the bottom, so that matched everything else, okay? So because it doesn't have that, that's all it's going to pass. Okay, so let's take a look at filtering local traffic. You can put a filter on the loopback interface to filter local traffic. So that is possible. You have to be careful that you don't filter out your routing protocols. Though, look at this one here. So here's a filter, which is limit SSH access term. Is SSH accept from source prefix list trusted, and we've got a prefix list that we have created. So from trusted protocol TCP destination port SSH, then accept, and we're going to reject SSH from everything, all other SSH, we're going to reject. And then we've got this else except term on the bottom, which accepts everything else. And that's us applying the filter onto the interface. Okay, little note here says, what if we forgot to put the else except on there? What would happen is nothing would get into our router, because potentially we would block out all other traffic, including routing protocol traffic and anything else, if you left that out. So that would be the issue. Let's look at the concept of policing or rate limiting. So this allows us to limit the amount of traffic that passes into or out of an interface. And it's just kind of a firewall filter. We can work with firewall filters to try and prevent against DOS attacks. Common actions include discard and setting loss priority levels, and we can use average bandwidth and maximum burst size as our parameters in this particular filter. So this is to limit the bandwidth. So here we have, this is a policer, it's called P1. The policy says, if exceeding bandwidth limit 400K, burst size 100K, then discard. So that's what our policy says. Then here, this is our policer, and then here's our firewall filter. It's called rate limit subnet. From match subnet source address, so there's the source address we're matching. Then, if it matches that address, then apply this policer. So we're going to limit any traffic from that address to the parameters set by that policer, and then the term is else then except. Okay, so we're going to be policing traffic from a particular subnet. Okay, so that is the use of a policer. So you can use the policer in conjunction with a firewall filter to identify traffic from a particular source address or range of source addresses that you wish to apply those policing constraints to. Okay, let's do a little case study here. So, we have our objective here is we want to discard and log all outbound traffic with any source address not belonging to 172.27.102.0/24. That's outbound traffic. if we have a look at that particular address, 172.27.102.0/24, that is the internal address of this particular network here. So the source address you would expect would be, or should be, from that network, shouldn't it? I mean, it should be from that network. If it's not from that network, and if it's outbound from that network and has a different source address, then something is amiss with that traffic. Okay. Inbound traffic. Discard and log all inbound traffic with a source address that belongs to 172.102.0.24. Okay, now think about that for a minute. If traffic is going to an address of 172.27.102.0/24 and has a source address from the same network, what does that tell you? Well, that tells you that is spoofing traffic. Okay, that is spoofing in action, if you do find that. So someone is trying to pretend that they're sending traffic from inside the network when they're actually sending traffic from outside the network. That's a hacking strategy. So we're going to allow all return traffic from the internet for TCP sessions initiated from MyNet. So anything initiated in MyNet, we're going to allow return traffic for that. Allow ICMP traffic that includes echo replies, time exceeded and destination unreachable messages, and discard and count all other traffic, and apply the filter to GE001. Okay, let's look at how we do it. So first of all, here is our filter. This is our out filter. We've called it deny spoofed from source address 0/0/0, so that's what it matches everything. And then we have an accept statement, 172.27.102.0. So in other words, the traffic can come from anywhere except that network. Okay. So this is our outbound filter. So we're matching everything except that. So if it matches anything except that, we're going to discard it. So in other words, you could say we're not going to discard traffic from 172.27.102.0/24, but we are going to discard everything else. And then we want to actually else accept. We're going to count outbound accepted traffic. Fine. So we're going to count the traffic as it goes out. It's all good. Now we've got our input filter, deny spoof, source prefix, internal prefixes. Now I have got a little list over here, which is a prefix list called internal prefixes, where I have got my internal prefix set up over there. The beauty of using a list in a filter is that if I ever want to add prefixes into my filter, all I have to do is go over here and edit my list. I don't have to mess around with my filter itself. I just kind of add stuff to my list, and we're all happy. So we can discard that, and then from protocol TCP established, then accept, and term allow some ICMP, and we're looking at exactly what ICMPs we're allowing there. Echo reply, time exceeded, unreachable, then accept. So that's our filter that we've set up. Okay, and let's apply the filter to the interface. Here we are, TE001, and there's our filter, input FF, and output FF. So there's our filters there that we've applied them. Of course, we commit those, and then away we go. We can monitor the results, show the firewall log. Well, if we go over here, we can first of all look at what was inbound discarded. We can do show firewall counter filter, output FF, output accepted. We can see what was actually accepted, and we can show the firewall log, and we can see exactly what was counted and what was recorded in that log. Okay, so that was us setting up a firewall filter. Here's another little thing I just want to look at. This is the last thing for the day before we wrap up. A thing called unicast RFP check. And really, this is an anti-spoofing defense as well. Because as you know, what spoofing does is it masquerades as traffic that's coming from a different source address to what it's actually coming from. And the purpose of that is to try and get through your firewalls, so that if your firewall says, I'm not accepting traffic from any of these addresses, it looks like it's coming from somewhere else, so it actually gets in through your firewalls. So we have this thing called unicast RFP, and it is an anti-spoofing mechanism. We have strict mode and loose mode, and with the strict mode, we're going to accept the packets. The packet source address matches an active route. The next hops of the active route uses the interface on which the packet arrived. And the loose is accept the packet if the packet source address matches a prefix in the routing table, and if the default route is present, packets always match the loose mode. So that's the downside of that. Okay, so what we're doing is we're using the routing table as a mechanism to decide whether or not the traffic that's coming in through an interface is legitimate, because if the source address of the packet does not match an active route, what that means is that we don't actually have connectivity to that network, so how could we be getting traffic from it? That's what that means. In other words, it's probably dodgy, it's probably bogus. Okay, so if we don't have in our routing table any connectivity, any information of how to get to that network, we can't possibly be getting traffic from that network. And the next hop should use the interface on which the packet arrived as well. All right, so when we're looking at this Unipass RFP, there's a couple of things we think about when we're setting it up. Is there may actually be more than one legitimate path to a destination network, in which case you would have to add the parameter feasible paths when you configure it, which means that it will not drop the traffic if there is a feasible path to the network. And with fail filters, process traffic that fails the RFP check, allows you to accept, log, or count the traffic normally denied, but you have to permit DHCP or bootp traffic, which is denied by default. So you have to actually reference that in your filter there and allow that traffic through, because that will not be in your routing table. Okay, and here's an example of setting up the unicast RFP. So we have got family oriented RFP check as a filter. So we basically just apply that little parameter there, and that will go ahead and set that up. And we can then put a fail filter in there, RFP DHCP, on the internal interfaces to allow DHCP traffic to still come through our internal interfaces. Don't need it on our external interface. Okay, so in this chapter, we looked at the framework of firewall filters, discovered that they were pretty much like access control lists. We looked at how we evaluate a firewall filter, the fact that we have got matching criteria, which is the from statement. We've got the then statement, which is the action. So basically a term is built on a matching criteria and a then statement. Identified situations where we might want to use firewall filters, wrote and applied it, and had a look at this thing called unicast RFP. Okay, so review questions. What are some common firewall filter actions And what does each of them do? So there were three common actions. What are the three common actions? First one starts with A. Flow control, no, that wasn't one. Accept. So we can accept, that's an action. What's another action? Discard. What's another action? Reject. What's the difference between discard and reject? The difference is discard drops the packet silently, reject sends a message back saying unreachable, or saying, actually what does it say? What does it say? Sends a message back saying no, not allowing this traffic through. Okay, and what is the purpose of unicast RFP? What are we trying to do with it? What are we trying to prevent with unicast RPF? Saying it wrong. Unicast RPF. What are we trying to prevent?
Prevent the package that is not from the active root or is not connecting.
So essentially, we're trying to prevent spoofing. That's what we're trying to do, which is a hacking strategy. Okay. Unicast reverse path forwarding is what it actually stands for. Yeah, we're preventing spoofing. Okay, very good. So that I think will do us for today. You've got some labs to do. Let me know if you have any problem accessing your lab environments. I think next week we will have our lesson back at the ACIT campus next week. And because there's some things I want to demonstrate and show you, and it's just a whole lot easier to do it from there because I can get into some active routers and demonstrate that stuff. Okay, so I just want to be able to do that from there. All right. So we'll have our lesson back at the ACIT campus next week. See you then.